All right, so we're going to start a bit with just some general requirements of all lithium-ion rechargeable batteries, which the hazardous location standards build on top of. At minimum, protection circuitry within a lithium-ion battery has to protect against excessive charge and discharge current, overcharging of the cells where they're charged above their maximum rated voltage, discharging the cells below their minimum rated voltage, short circuits, and charging outside of the rated temperature range. The circuitry is usually or always integrated into the battery by way of the battery management system. In kind of standard lithium-ion packs, it's not uncommon for the temperature protection to be handled externally through a thermistor that is connected to the application device, but that sort of external protection typically isn't viable in a hazardous location battery. So that really needs to be considered. One other thing to keep in mind when designing the device is that you should integrate some form of under voltage lockout on the battery input within your circuitry as well. The thresholds within the BMS are usually set to keep the battery safe, but not necessarily keep the thing operating within a range that makes it last as long as possible. If you'd like to learn a little bit more about the more general safety requirements of lithium-ion batteries, we have a previous webinar you can take a look at, which covers this in more detail. That QR code there should take you there. All right, so on top of the minimum safety circuitry, batteries used in hazardous environments typically fall under IEC 6079, specifically 6079-0 and 6079-11. Both ATEX and IEC align with these standards, and the markings for them are often combined. Within 6079-0, there's a clause that requires that cells be connected only in series. However, within 6079-11, there's a statement that allows them to be connected in parallel in intrinsically safe apparatuses, provided that intrinsic safety is not impaired. So it can be a bit of a loaded one, where it's often easier to avoid parallel connections in an intrinsically safe device, but it's also not impossible to get certified either. A bit of a balancing act between voltage and capacity, as the total voltage of the battery also reduces the allowable current limits. So the higher the battery voltage, the lower the allowable peak current. All of the cells used within the battery have to be of the same type and manufacturer. It's not possible to mix cell types for things like increasing pulse currents. Really, this isn't typically a huge concern. Packs really are usually only made with a single cell type anyway. And also only certain cell types are allowed to be used within these batteries, and they're specifically called out in the standard. Again, really not a huge concern for most things, since all of the typical chemistries are included in the standard. What they're really going for here is that you need to stick to established, well understood chemistries where the failure mechanisms are understood, well known. And you're also not allowed to exceed the manufacturer's recommended operating limits, regardless of what the battery was tested to under the standard. So as an example, it'll be tested to peak surface temperatures way above the recommended operating conditions. And just because it passes that test doesn't mean you can do that intentionally or repeatedly. The hazardous location certifications are typically done at the system level, with battery really just being one component of the whole. It's important that the certification strategy for the whole system includes the battery. We recommend involving the battery design team early in this process to kind of contribute to your certification matrix. Things like protective circuitry within the charger or device can influence what needs to go into the battery, and sometimes it makes sense to shift things between parts of the system. So really all that to say there's kind of no one size fits all answer, and you really need to work in concert with your test lab and battery manufacturer to come up with a strategy to make sure everything gets done correctly. Moving on to the markings. We're going to kind of walk through the markings here as a way to cover all of the specific requirements. There's an example set of markings on the bottom of this slide. These are really just placeholders, and any specific markings required for your application will depend on the environment that the thing's going to operate in. We'll walk through each of them, cover what they mean, and how that impacts the design. So there's kind of two groups to these markings. There's the ATEX prefix and the IEC portion. We'll cover the ATEX prefix a bit, but we're mostly going to focus on the IEC section since they're most relevant to the design of the battery. There's two rows, top row for gases, bottom row for dust. The ATEX prefix starts with the CE mark, and that mark includes a notified body number. In this example, it's D0539. The EX symbol is next, followed by the equipment group. Group 1 for mines, group 2 for everything else. Following the group is category, M1 and 2 for mining equipment, and categories 1, 2, and 3 for all other things. And these kind of indicate the level of protection offered by that equipment. You're allowed to use equipment certified to operate in zones more hazardous than needed. So what that kind of means is category 1 can be used in zones 0, 1, and 2. Category 2 can be used in zones 1 and 2. Category 3 can only be used in zone 2. And the differentiator there is the likelihood of the hazardous atmosphere being present. So zone 0, hazardous atmosphere is definitely present. Zone 1, it's likely to be present. And zone 2, it's unlikely to be present. And finally, the last character there aligns with the previous slide, and just top line for gases, bottom line for dust. EX, again, is just the explosion protection indicator used by both ATEX and IEC EX. And these ones are where things kind of start to get interesting. The type and level of protection end up driving quite a bit of the design. For a battery, it's usually intrinsic safety and a level of protection of either IA, B, or C, with IA being the most stringent and IC being the least. The main concept here is limiting spark energy and surface temperatures to prevent ignition. The ways you're allowed to go about the limiting of current and spark energy differ with each level of protection. For example, for IA, at most voltages, it pretty much has to be some sort of resistive current limiting, whereas IB and IC are a little more permissive. One thing that's pretty important to be aware of, especially in IA with the resistive current limiting, is that it can result in a pretty large voltage drop as your currents approach the limit. We've seen this one bite a few people in the past. If you haven't accounted for it, it's entirely possible to paint yourself into a corner where the battery can't supply the energy required to either start or run the device at all because the series resistance causes the battery voltage to fall so low under load that it's essentially useless. So one potential trap to be aware of. There's also varying levels of fault tolerance. So we go back to the place. So also varying levels of fault tolerance must be designed into it, also depending on the level of protection. So for IA, again, which being the most stringent, it's typically 2 faults for critical items, meaning your circuitry for these things must be triple redundant. The faults will get applied to the circuit during testing and analysis and cannot change the safety of the product. So, one thing they'll do is short out FETs or protected devices just to make sure that they can fail safely and the battery is still intrinsically safe. Next are the hazard groups. There are 3 of them. Group 1 for mining, where methane and coal dust would be the most common hazards. Group 2 for gases, vapors, or mists in above ground industries. Within group 2, there's 3 subgroups. 2A for gases like propane, 2B for ethylene, and 2C for things like hydrogen or acetylene. The hazard group under which the equipment ends up getting classified really is one of the factors that determines the short circuit energy. As I'm sure you can imagine, the gas or dust type present in the environment alters the energy required for ignition. So permissible short circuit energy gets calculated on the circuit as a whole, not just the battery. And it can pretty significantly limit the amount of capacitance and inductance you can have in the circuit. Much like the current limiting thing, it can also impact the functionality if it's not properly considered. Just like category, equipment with a higher level of protection than required for the hazard class can be used, just provided the environment does not have an ignition temperature below the equipment limits. We'll get into the temperature classifications a bit in a couple slides. One of the common strategies for reducing risk is some form of potting compound. It can be used to reduce the required clearance distances internally between coatings. Within the standards, it's table 5 Annex F. The language they use there is distances under coatings, casting compounds, and through solid insulation. And they can allow you to compact things quite a bit versus things not being potted. Likewise, in cases where straight clearance distances are used, the enclosure has to prevent ingress of things that could break down those distances, such as liquids or conductive dusts. And the boundaries, the outside of the enclosure, get defined by the manufacturer and need to be documented accordingly. One thing that we really need to mention when thinking about potting a battery assembly is that the venting mechanism and CID really shouldn't be interfered with. In the case of a lithium-ion cell, it's part of the positive terminal, and as the pressure inside the cell increases, it interrupts the current. If you fill that with potting compound, it can't function, so you usually have to seal that off in some way. And here are the temperature classifications. For some reason, they call them out differently for gases and dust, though they're typically certified to the same temperature. So in this example, we have T5 for gas, which corresponds to 100 degrees C, and dust is also 100 degrees C. Again, the temperature classification that the battery must comply with really depends on the whole product, but often T4 or 135C are the most common in our experience. One of the tests required here is a short circuit of the cells with a resistance of less than 3 milliohms. The cell is shorted until fully depleted, and in the case of an unpotted assembly, the surface of the cell is not allowed to exceed the temperature specified, as in the last slide. For levels of protection IA and IB, this testing requires that the cells be made without protective devices in them. For cylindrical lithium-ion cells, these protective devices are usually PTCs in the headers, and those are essentially resettable fuses. So the reasoning for needing to have them produced without them is that the PTC would activate and prevent the cell from being fully depleted before reaching its peak temperature. So if the cells selected have a PTC, your battery manufacturer needs to have kind of a strong enough relationship with the cell vendor to be able to work with them to make those modified cells. One thing to be aware of here is that it can often take quite a while, as you might need less than 100 cells produced like this, and they've got to be built on a pilot line. Because the peak temperature of the cells is so important, we really recommend doing the short circuit test first and like really early in the design cycle. We'll usually send cells to the lab as soon as we know what we want to use in the battery, way ahead of the design being complete. If there are any issues with the test, and the peak temperature happens to exceed the limit, the scope of the entire project will change. So it's really best to do that as a pre-qualifier. It's not super expensive to have it done on its own. And we often do a round of it in-house before sending cells to the lab as well, just to have decent confidence that it will pass. Removes a fair bit of the risk in getting it wrong. The cell types that are most likely to pass are those with lower capacities by kind of current standards. Few mechanisms at play. Lower capacity cells really just have higher internal resistance, meaning their short circuit current is lower, and less capacity means there's less energy to deplete. And finally, in the markings is the equipment protection level, which dictates which zone the device will be used in. So we kind of covered those zones previously, but again, also comes from the intended operating environment. So with that, I think we'll hand it back to Charlie, who will take us through a bit of a Q&A period. Thanks.